let's begin. So I want to start with, I guess, number 1. That was as good a place as any. I'm just setting up my colors here so that they'll actually show up because I'm doing this all on white and not on the black color that I normally do. And there we go. All right. What is the speed of the car when it's traveling at its fastest? Now, looking at this, we're eventually going to have to figure out the speed of the car here. That's when it's at its fastest. I think we're going to be finding the speed of the car here. I'm pretty sure we're going to have to find the speed of the car here. And eventually we got to find the speed of the car here. Let's just do all of that right now. Is that okay? All right. So they're labeled B, C. Let's just make this D and E. Is that all right? So the energy at A has to equal the energy at B, has to equal the energy at C, has to equal the energy at D, has to equal the energy at E. If there's nothing that takes the energy out of the system, all of these have to be the same. So we can pick any 2 of these and set them equal to each other, but we have to be given enough information to figure out at least one of them. So let's face it, we have to have enough information to figure out at least one of them. But let's consider at A, which is here, what kind of energy do we have? Gravitational potential. I will remind you quite nicely that there's 3 kinds of energy that we've talked about so far this year. There's gravitational potential, there's kinetic, excellent, and then there's elastic. There we go. All of our forms of energy. So above the reference level, moving, pushed back against a spring. All good? All right. So now I'm going to, I think, establish our reference level. How many of you are good with that being our reference level? That good for all of you? All right. Are we above the reference level at A? Yes. Are we moving at A? Does it say? It says we have released it from rest, so not moving. Are we pushed up against any springs at A? No. All right. Let's take a look at the energy we have at B. At B, that's here. Are we above the reference level at B? Are we as high above the reference level as we were at A? No. So if we made our little graph, the potential energy bar for this one would be really big, but the potential energy bar for this one would be less big, right? So where's the rest of that energy? Kinetic. So there must be a kinetic energy bar that's like this big. Yay! So I hate this stuff. Bye. But if you buy into it, yay. So I'm going to put plus kinetic there. All right, at C, we are here. And I'm going to point out that I'm not even going to bother because B and C are the same because it's the same height, right? Just keep in mind that whatever we find out for B, it's going to be doing the same thing at C, same height. D is right here. So are we above the reference level at D? No. So there's no gravitational potential energy. Is it moving at D? I sure think so. That makes perfect sense. And lastly, at E, are we above the reference level? Yes. Are we moving? Yeah, we're not as high as we were at the start, so whatever remaining energy there is, it must be dumped into kinetic. Alrighty. Let's just consider that here, the height is 1.5. For B and C, the height is 0.5. And for D, the height is 0. And for E, what's the height at E? 1, yeah, because it's a radius. It's up there, right? So it's got to be 2 times 0.5 or 1. Let's go. Let's find all those speeds, right? We can find everything. So go ahead.
I have a question for like B and C. Do you just, because they're the same height, you don't write another UG plus K, you just leave?
I could have. I'm just not going to do the problem twice.
Okay.
I'll show you. Let's do that one first. Let's find out the speed at B, okay? We're going to do the speed at B. How high are we at B?
0.5.
All right. So we start off with mgh, where h is 1.5 above the reference level. That equals the speed at B is mg, well, that's 0.5 above the reference level, plus 1/2 mv squared. This would be finding the speed when we were at B. Now, if I want to find the speed when we're at C, well, we're still comparing it to where we started, 1.5. But what is the height when we're at C? 0.5. That's right. So this will be 0.5 plus 1/2 mv squared. You notice that we're going to get the same thing.
Yeah.
So I'm not going to do the problem twice. Let's do it once and say it's the same for both B and C. Now, they're going the same speed. They are not going the same direction. If we look back at our picture, B is going this way, C is going that way, but they'll be at the same speed. Okay? So let's just do this one real quick. The m's cancel out because there's one in every term. So I will get 15 equals 5 plus 1/2 v squared. That looks to be v is the square root of 30, or 5.5 meters per second. No, square root of 20. What am I doing, Mr. Shelton? You should expect better of your leaders. That's 20. And that's 4.5. There we go. Now I'm doing math better. 15 minus 5 is 10. 10 times 2 is 20. All good? You're confused? Then you should say something. Where? Okay, so I will do more math. Which math do I need to do?
The 15 equals 5.
Okay, so you're good with me getting to here. Like you're good with this. So I will subtract 5 from both sides. And then 15 minus 5 is 10. I will multiply both sides by 2. And then I'll take the square root of both sides. That better? Okay. Now, do you see any reason for us to repeat that at C? Or just say this is the velocity at B and it's the velocity at C. That okay? All righty. Let's go on to the next part of this. We wanted to find the speed at the lowest point. So the speed at the lowest point, let's see what we got up there. The lowest point is when we're at D, right? D is a height of 0. But we still are starting with the same amount of energy. So mgh, which is 1.5, equals 1/2 mv squared. You see, in this one, I don't have any potential energy over there because my reference level, I'm on the reference level. So mgh is just mg times 0. So cancel the m's again, and I'll get 15 equals 1/2 v squared. So v squared equals 30, and v equals 5.5 meters per second. This is the velocity at the max, it's fastest. It's at D, the bottom. Still okay? Last one, let's find out the velocity at the top of that loop. That's when the height is 1.0. So I'm going to do mgh GH, where H is 1.5 again. This is the one I know, so I'm starting back here every time. That's going to equal mgh, but h now is 1.0 because we are 1 meter above the baseline, plus 1/2 mv squared. Again, it just so happens to be an m in every term, so I can go cancel them all out. And I'll have 15 equals 10 plus 1/2 v squared. Subtract 10 from both sides and get 5 equals 1/2 v squared. So 10 equals v squared, or v equals 3.2 meters per second. How was that? I am excited to answer it.
So, were you equal?
All right, they told us the height that we started it at, right? So that's how much energy we have. And I can use that over and over again because we never lose that amount of energy.
Right, okay.
Does that make sense? Okay.
So we can do that for every problem?
You're going to be given the energy of some point in the problem. They're going to tell you the energy of some point in the problem. It doesn't have to be at the start. Like, what if I told you instead how fast you were going here? Well, you could work backwards to figure out how high you must have started, but you would still have the energy to apply to other parts of the problem, right? I've just given you a different place where you have the energy. So they have to give you the energy somewhere, or at least enough information to surmise what the energy must be in the problem. For us, they gave us the starting height. So they gave us a place to start. They gave us the energy at the start of the problem. And any problem like this, and I can make up one that's similar to this, where we're given the energy from someplace else in the problem, and then you'd work around that to see how you would get the energy for different places. But again, I got to give you something. Like, remember the one we did just the other day, where I asked you to find the minimum speed here. Remember that? Once we found the minimum speed here, we could figure out how much energy you have to be there, and therefore how much energy the system has to make sure you go all the way through the loop. That's a problem we can do too. I have a good example of one we'll do in a minute, okay? But let's get through this one first. Unless you're done with what you need to know here. If you're done with what you need to know, I can finish now.
Can you go over another problem on the problem set 2?
I can, but I'm not going to switch this one and then come back.
Oh.
So if there's nothing left here, fine. Go ahead.
Oh, can you go over 8 and 9 and 7 on this problem?
Sure. I don't know what those are. So you had no trouble with the force part of this? Okay. Yeah, that's 4 and 5. You just asked for 7, 8, and 9. So I'm good to go to 7, 8, and 9? Okay. 7. What is the horizontal range of the car after it leaves the ramp? So here's what I'm going to do to make this easier on me. I'm going to get a big eraser out and get rid of all of this stuff. And point out that we know, at this point, the car's traveling at 4.5 meters per second. At this point, the car's traveling at 4.5 meters per second. At this point, it was traveling at 3.2 meters per second. And at this point, it was traveling at 5.5 meters per second. That's just all the information we got from what we did earlier. All good? Well, once this object leaves the ramp, it is a projectile. And we need to use projectile motion to solve for it. As I said earlier in the year, there's no replacing projectile motion. So that's that vertical and horizontal stuff. Remember? Nobody likes it, but that doesn't matter. That's what you have to do. So delta y, v initial, v final, a and t, and r Vx and t. Looks like delta y is 0.5 meters. I started here and I'm landing here. What's that? I haven't decided what direction is positive or negative yet, but we can go ahead and do that. So Oliver wants us to go ahead and use upwards as positive and to the right as positive. I'm good for that. So that would make that negative. All right. Moving right along, the initial velocity, well, that's going to be 4.5 sine 30. Do you remember how to do that? Should have that little chart somewhere. We don't forget. We just, don't use it all the time. Acceleration, negative 10 meters per second squared. And Vx is going to be 4.5 cosine 30. We have to find the time here. Plug it in over there. Now, I'd love to say you guys can do that. I know that that's a struggle bus for some of you. So delta y equals 1/2 at squared plus dy initial times t. Keep going. We have to find the time. How many of you know how to do this with your calculator? Like, can you use the calculator to find the time? You guys have those calculators. None of you? Oh, we should learn. Don't you want to know? Let's plug all the numbers in real quick and get a relationship. Delta y is negative 0.5. That's going to equal 1/2 times negative 10 t squared plus Vy initial is 4.5 times the sine of 30. So that's got to be 2.25 t. Any questions? Because this is where you should ask questions if you have some, because we're gonna switch gears here in a minute. All right, 0 equals negative 5t squared plus 2.25t plus 0.5. All right, got those calculators handy? So t equals 0.6 seconds.
I'm just gonna give up.
You're gonna give up?
On my calculator, I'm giving up.
That's quitter talk.
On my calculator, she's just.
Oh, it's 0.4.
Yeah.
What are you getting anyways?
Am I getting?
Are you getting anything?
I'm getting 0.757.
So there, we got it. Oh, wow. Yes, I expect that you guys remember how to do old stuff. Yes, it can be on the test. And yes, there's other things we should talk about today. So, when you build this and test it with a real car, it is found that the car is only going 2.5 meters per second at point C. We say it's supposed to go 4.5 meters per second, but it's only going 2.5 meters per second. That's weird. That's not what we expect. We should check, and we're going to. How much energy does the car have when we start the ball or start the car? That's here. The actual amount of energy is mg h minus h naught. And we have the mass of the car. What is it? 0.5. It's 2 on the next problem. G is 10. H is 1.5. Correct? So you multiply all those things out, and what do you get? 7.5 joules. That's how much energy it should have here. However, they say that when we're there, we have mg, h is 0.5, plus 1/2 m times 2.5 squared. Right? Instead of 4.5, I'm putting in what they say the car has when we get there, a speed of 2.5. So 0.5 times 10 times 0.5 plus 1/2 times 0.5 times 2.5 squared. You gotta do all that. Yes.
I'm just clarifying, we are using those two equations because of, that's what we got for C and B.
We're using those two equations too because we know the object has both potential and kinetic energy here. They told us how fast it's going, and we know it's above the reference level. All good?
Yes.
All right. So that's 2.5 plus, oh, I don't know. That sounds like a job for a calculator. 2.5 squared is like 6.25. Then I want a quarter of that. And that's, I don't want to do it. I'll just do this. 1.5625. So I get a total amount of energy of 4.06 joules. Is that a problem? Yes. How much are we supposed to have?
7.5.
7.5. How much do we actually have? So, friction must have done work on the car. How much? Subtract these two. Minus 7.5, and I get that friction must have done 3.4 joules of work. And it has to be negative. It took that energy out of the system. Bye-bye, energy. Now, any questions about that? Question 9, we didn't talk about power, so I wouldn't expect you to be able to do it, and it won't be on your test, but power is work over time. So all you'd have to do is take 3.4 and divide by 1.1. But I'm not expecting that on your test. They're telling me how much force, they're telling me the angle they apply the force, they're telling me how far they apply the force, and they're telling me the mass of the skateboard. So I have a whole bunch of stuff. There are other forces acting on the skateboard. There's a normal force, there's weight, but the work done on the skateboard is just going to be the applied force, 5 newtons, times the displacement, 2.26, times the cosine of the angle between the force and the displacement, 37 degrees. That's our definition of work. So 5 times 2.26 times cosine of 37 equals, I get about 9 joules. Any questions about that? That's how much work was done on a skateboard. How much work did the normal force do? Ooh, that's a good question if you guys don't have the answer. I should ask that tomorrow.
Yeah.
How much work did the normal force do? It is 0, because the normal force is perpendicular to the displacement. How much work does gravity do? 0, because gravity is perpendicular to the displacement. All right, so this is the total work done on the car. That means the car now is over here, and it has 9 joules of energy. What is the change in kinetic energy of the skateboard? 9 joules. We just said that. This is the net work done on the car. That is the change in kinetic energy. How fast is the skateboard at the end of the 2.25 meters? Look, I'm not going to find out how much work was done in 2.25 meters. I'm just going to assume it's about 9 joules. Is that okay with you guys? So that means 9 joules equals the change in kinetic energy. Or 9 equals 1/2 mv final squared minus 1/2 mv initial squared, and that's 0. So this will tell us how fast it's going. So I got to do some math. The mass is 2, so this velocity just ends up being 3 meters per second. The skateboard hits a curved portion of the course that causes the skateboard to be propelled upwards. What is the maximum height achieved by the skateboard? Well, can we all agree to make this the reference level?
Yep.
So we only have kinetic energy here, but when the car makes it, say, to here, the highest point will be when the kinetic energy is 0, right? Do we understand that? We have it in our notes that the highest point in this case is when the kinetic energy is 0 because it's no longer moving up or down. So we have all gravitational potential there. Well, that seems pretty straightforward to me. So that means here we must have 9 joules of energy. And that has to equal mgh minus h naught. So 9 equals 2 times 10 times h minus h naught. So h minus h naught equals 9 divided by 20, which is 9 divided by 20 is like a half, 0.45. It is 0.45 meters above. All right. If instead we lift the skateboard 3 meters above the curved portion, so way up here, which is now 3 meters above the ground. Well, how much energy does it have? Well, 2 times 10 times 3, or 60 joules of energy. That all good? Are we okay over there?
Where did we get the 2?
All right. What's that? The mass is 2. Is that okay?
Yeah.
When we drop it and it comes back down here, it's going to be zooming now, right? Because it has a lot more energy. How fast is it going to be zooming? Well, that 60 is going to equal the kinetic energy at the bottom. So that's going to equal 1/2 times 2 times v squared. So v equals the square root of 60, which is 7.7 meters per second. That's where the 7.7 came from. I knew it had to be somewhere. Now this last one, we're almost out of time, but this is an important one, I think. It's an area where there's grass. So the car is right here, and right now it has 60 joules of energy. And it's going to go here where it will have 0 joules of energy. That seems like a change in kinetic energy to me of 0 minus 60 joules, or negative 60 joules of energy was taken away from the car. That was work done by friction, because friction is acting this way on the car. So, friction times displacement times the cosine of the angle has to equal negative 60. We all good? Got 10 more seconds. Friction times 10 meters, how far the car travels in the grass, times the cosine of 180 degrees, because friction is to the right, but the car is moving to the left. All good? Equals negative 60. So, seems to me friction is going to be 6 newtons. And considering that mu is friction over the normal force, mu is going to be 0.3.